Okay, sorry for the delay. I'm having a couple of technical issues going on here. I don't know why. We'll figure it out. Okay, so we're talking about supercritical fluid. So supercritical fluid is going to be that phase. If you guys take a look, it's going to be that phase between a liquid and a gas, right? And so the thing about your supercritical fluid, it's going to have characteristics kind of both states. Okay, like a gas, the supercritical fluid is going to be able to expand. It's going to be able to fill a container. And then it's going to have its density characteristics are going to be kind of closer to the liquid. Okay. And so your critical point is going to be that pressure where your supercritical point, critical point is going to be the point where you reach your supercritical fluid. Okay. It would be sort of like the cloud, not the rain. Yeah. So it's going to be like a cloud. So when you guys are sitting there talking about this, talking about your experiment, you guys are actually trying to get your fog. It's like a supercritical fluid in that case. It has both those characteristics because in it has that moisture, and then it also has the concept of the gas. It's expanding like the gas does. Okay. So supercritical fluids don't exhibit any surface tension. They have very, very low viscosity. They can be dissolved in non-volatile solutions. And they can penetrate small openings, you know. And so if you kind of think about that fog can kind of seep into things, right? So, and so one way that supercritical fluid is used is basically it's used to extract caffeine from like beans, coffee beans and stuff like that. So it's used in that context. And it's kind of nice because, you know, caffeine has both polar moieties and non-polar moieties. And so it makes that extraction even that much better. So. Okay. And so you guys are still familiar with the phase diagram, solid, liquids, and gas, and then that's your supercritical. Questions? Okay, solid materials. So solids can be broken down into two types of solids. We have a crystalline structure, and we have amorphous structure. Amorphous is basically lacking order. Crystalline is order. So I often like to use the analogy of Mystique from the X-Men, shapeshifter, right? So she kind of lacks order in the sense that it's not a set way, you know, so. Okay, so this is an example of a crystalline structure. That would be amorphous, okay? And so here, crystalline, amorphous, right? Yes, crystalline has a very defined pattern, okay? And that's going to be important for kind of understanding solids. Now, here, this is silicon dioxide. So it's quartz, okay? Now, quartz is organized, right? It's very organized. And so like the quartz that we see, we'll see a nice little crystal, you know, those fake diamonds, right? You guys seen fake diamonds? Well, believe me, I have a lot of those, right? So give them to all the girls. So I'm joking. So those are very organized. There's very organized pattern that's associated with it. Now, here we have, this is not a metal, this is a compound. This is actually an ionic compound, right? Or not ionic, it's a covalent compound. Because it's silicon dioxide, right? So, but it's a compound that's organized in a crystalline form. Right? And then if we take that quartz and we heat it up and we cool it down rapidly, we're going to end up getting an amorphous, right? And then we end up with fused silica, which behaves differently. It doesn't have a nice crystalline structure, that nice diamond-like structure that we see, right? It looks like gunk, really. So an ionic, the types of solids that you guys are going to encounter, there's going to be ionic solids. So an ionic solid is kind of like salt. Sodium chloride, it's bonded together by ions. So in that case, you have order that's associated with it. You know, you have your sodium, your chlorine, sodium, your chlorine, your sodium, your chlorine, your sodium, your chlorine, right? Alternating with each other, okay? So ionic solids are going to be hard, they're going to be brittle, they're going to have a high melting point. They're not going to be able to conduct electricity unless they're molten, which is melted, right? Or dissolved into solution, okay? We have metallic solids. Metallic solids are mostly going to be crystals. They're going to be uniformed, and then they're going to basically use, you guys remember when we talked about metallic bonds, where the electron is dissociated? Kind of, not really. Okay. Okay. What was that? I said, do you guys remember when I talked about metallic bonds? Metallic bonds? Metallic bonds. Yeah. Yeah. Well, in a specific way, but we'll go over real quick. So in the case of metallic bonds, what happens is that, let's say, for instance, we're talking about sodium metal, right? Sodium metal, we know that sodium has that one electron, right? This one electron that's associated with, right? And A has that one electron, right? You guys remember that? Okay. So what it does is it'll go, and I'm just going to make a little ball that represents sodium. So this is my sodium ball, right? What it does, it will take that one electron and drop it off like right next to it, okay? And then sodium is going to be plus, and the electron is going to be minus, right? And so it's going to pretend like, oh, you know, that's not mine, but that's negative, I'm positive. Oh, yeah, we can get together, right? And then the next sodium does exactly the same thing. And the next sodium does the next same thing. So you have this bonding that occurs because it's dropped its electron, okay? So that dropping of its electron is called delocalized electrons. So it forms like a sea of these delocalized electrons until the sodiums are sitting there, so it kind of keeps it intact. Okay, so metals stay intact that way. That's how they bond with the other elements of that metal, right? Yes. Ionic solid, it would be like sodium chloride. So this is sodium, Na, and then this is your chloride, Cl minus. So that's Cl minus, that's Na plus, right? So it's the full atom, right? Because that's positive, negative, positive, negative, positive, negative, positive. Where this here is just taking that sodium, this is sodium, right? Normally, then sodium, what it does, it'll make a plus, make itself plus, and drop its electron next to it. Yeah. Well, yeah, that's what this is, a metal and a non-metal. Yeah. But it's alternating, but they're charged. Okay, and that's what is the ionic component. Yes. Well, no, you could also get alloys, right? And we'll talk about that. And so that's one of the things about metallic bonds. So like you guys, 24 karat gold is 100% gold, right? 18 karat gold isn't. 18 karat gold is mostly gold, but you have a little bit of silver and a little bit of nickel, right? And they do that because, well, it's cheaper, right? You don't have to use pure gold. And it still uses a metallic bond, right? To sit there and make it happen. Okay. So, yeah, you could just put it up there. It was left by one of the students. Okay, now, the thing about metals, we know that they're highly conductive, right? So we put electricity in it. Guess what it does? You'll put electricity on the other end. You hold a piece of metal, electricity coming in on one side, you shock yourself, right? Okay. And also the same thing with heat, right? It's very conductive with heat. That's why we use metal pans. Right? Metallic metals have luster, right? They're kind of shiny. They have a shininess associated with them. They're malleable. Malleable kind of means that, we can bend them a little bit and stuff like that, right? So we can pull them apart, stretch them, they have malleability. Have you guys gone to like an amusement park and they have that penny thing that you have to put $1 in to make it flat and get that emblem, right? You've never done that? Where you take a penny, you stick the penny in there and you run it through this machine and it flattens your penny? Yeah, and it engraves like a picture of Mickey Mouse or whatever, right? Or Jurassic Park, yeah. Okay, we've got to get you to an amusement park. That's a little different, yeah. So, but us being able to flatten it down, right, into that form, that shows you that metal is malleable. It's still connected, right? We still can sit there and we can wiggle it and stuff when it gets thin enough, right? That's malleability, okay? And metals are going to have various strengths. Certain metals are going to be stronger than others, right? Some of them are nice and smushy and you can push them with your hands, and other ones, you could chip a tooth with it, So, and they're also going to have different melting temperatures. Okay, so we can also have covalent networks. So when I talked about silica dioxide, quartz, that's an example of covalent networks. Okay, graphite, carbon, graphite pencils, right? Your pencil, ready using a pencil, that's graphite, right? So that is just a covalent network. Okay. A diamond. All of those are examples of covalent networks. So they all start off with, a structure, and it becomes organized. A diamond is very organized in its structure. It's just carbon organized, where graphite organized like this. And so this is the unit for graphite. This is the unit for diamond. All these are just carbons that are attached to each other in layers. Sorry. And then we could have molecular solids. So carbon dioxide, dry ice, right? That's an example of molecular solid. Or iodine, the little iodine droplets or before it solidifies. Okay, so in that case, you're going to have neutral molecules. They're going to rely on intermolecular forces for their strength, and then their strength is going to vary. Dry ice, it's a hard block when it's really frozen, but when you start heating it up, it's crazy. Sugar, right? Iodine. So those are all examples. You guys have that look? Are you good? Okay. So in the case of carbon dioxide, we know is nonpolar. We know that its melting point is negative 78 degrees Celsius, right? And then iodine, which is basically nonpolar as well, and its melting point is 114 degrees Celsius, right? So you have these two molecular compounds that behave quite differently from each other. Okay. This is just a table summarizing all the things that I've talked about. And again, it gives you an example of each. Okay. So a lot of these components have been used for tech stuff. Diamonds are often used. We use diamonds for lasers and stuff like that to focus lasers. Graphite, obviously, for pencils. We also have, here's an example where they're using a graphite wafer for certain techs. And then this here is called the buckyball. These are nanotubes, and these are stacked sheets. And these are just sheets of graphite that are being used in different ways. Okay. So technology has advanced quite a bit by using these different types of solids. You heard of graphite rackets, tennis racket, right? Really light, right? Rather than having to use aluminum, they use graphite. And so, yes. So, let's say, for instance, graphite, the graphite sheets or the graphite sheets, and a diamond, right? So, yes, the way that that carbon is organized is different, right? And let's go back here. Okay, so this is that graphite organization of carbon. This here is the diamond organization of carbon, right? Yeah. You said you thought. Yeah, but the thing is that the electrons, again, the electrons are here, they're like around the atom. And all of those are carbon atoms, right? And so they're like, in this case, they're covalently bonded to each other. Yeah. So this guy's forming a double bond, single bond, double bond, single bond, double bond between carbon, right? And so they're bonded together, right? And so they're forming a molecular, I mean, it has a molecular unit, but it's a repeated pattern in that unit, okay? And so that's the same thing here with, in terms of a diamond and graphite. Both of them are carbon, right? But it's how they're organized, right? And so they just consist only of carbon. Yes, because then you modified it and you're putting pressure on it and it causes that modification. You get coal to be a, yes, from coal, yes. Yeah, from coal, yeah. Graphite, well, graphite, it's harder to do. It takes a combination of pressure and temperature, because then to get that to happen. But for coal, it's just pressure. Yes. Yep. Yep. Okay. So now sometimes we have a defect in the crystal. The defect can be a result of various things. It could be a result of a vacancy, an open spot. Okay. It could be a result of a substitution. We have another atom that is about the same size that just kind of falls into that spot. It can be a substitution that is bigger that causes it to work a little bit, or it could be an intersensual substitution, which basically means that it's a substitution that isn't going to affect the lattice normally. It falls in between the lattice. So you see how we have this guy nicely organized and we put this little guy in there? Well, it's an impurity. It's there, but it's not causing a warp. Where this vacancy is an open spot, right? So time, if pressure hits it the right way, you can have that thing collapse. Or in this case, this guy's caused warping because it's a bigger atom, okay? So you'll have both of those possibilities that could be occurring throughout the process, okay? So a lot of times we take advantage of this because this affects the strength, it could affect the strength of the metal that we're working with or the solid that we're working with. It can also give it characteristics that'll make it a little bit different than others. Like for instance, we often will dope something, right? So have you guys heard of silica wafers? And it's p-doped or n-doped. So they either put phosphorus or nitrogen in silica wafers. What was that? Yes, yes. So silicon wafers for, yes, the CPUs. Now, they'll dope those to give it certain characteristics and have it behave slightly different under different circumstances. And so all they're doing is that instead of putting silica, where it's all silica, they'll put either nitrogen or phosphorus, depending what they're trying to do. Okay. So the other thing, like iron, right? You guys, iron is Fe, right? Iron. So steel, stainless steel basically has carbon. So it's doped with carbon. So we basically add carbon to add strength to it. And also it causes it not to rust, right? And was that? Iron? Yes, partially, yes. Yeah, it does change color. But there's also, the other thing is that what they do to make it just like, if you want strong iron, you put carbon in it. But if you want it so it won't rust or anything like that, you also dope it with chromium, right? So you'll add chromium. So you'll make it like an alloy with iron and chromium. Okay, so here, this shows us lattice points. This here represents the unit circle. Now, when we're talking about these metals or we're talking about these solids, they're organized in certain patterns, okay? And so what they've done, they actually have done a lot of studies on looking at the different ways of organizing. One of the simplest ways of organizing is a simple unit circle, where you just have your 4 points. So this would be an atom, 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 this would be an atom. That'll be an atom, okay? So that represents each corner that is an atom, okay? And then what happens is that you just have a unit circle stacked on top of a unit circle, a unit cell stacked on top of a unit cell, stacked on top of a unit cell, stacked on top of a unit cell. It is definitely mundane, let me tell you. I'm sitting there thinking about geometry. You're having talking about geometry earlier. I'm thinking about the unit circle. Yes, there should be copper wire. What was that? So lattice points are just the points of each of the corners, yes. So, and each of those are going to represent an atom, okay? Say, or a molecule, or, you know. Okay? So if we're talking about a metallic atom, this here represents each point of that atom, okay? And this is called a simple cube, right? Because it's what? A simple cube. Okay. So if you look at the simple cube, this shows you that each atom has 6 points of contact. Okay, so it has the one that's above it, the ones that it's across from it, the ones that are next to it, and the one that's below it. 6 points of contact. Okay, so it would have a coordination number of 6. This shows you just those lattice points. And then here you have 8 corners. Okay, so if we sit there and we take a look at this, right, and we cut the atom into just that unit circle, right, how much of each atom is going to be in that circle? I said, how much of each atom, not it's going to be in that circle, how much of each atom is going to be in that cube? Is it going to be half? Are you sure? A fourth, right? So then it should add up to a total of 1, 2, 3, 4. 1, 2, 3, 4. So it'll be a total of 2. That's right. So do you see it why it's a fourth? So think about a ball, right? You have a ball here on each corner and you're cutting it You're cutting it here, you're cutting it here, you're cutting it here, right? So the only thing that's going to be left is a fourth, because you have a face here, face on top, face on the side, right? So only a fourth of it's going to be left. That's right. So, so actually it says an eighth, not a fourth, right? So it'll be an eighth because it's top. We have the top here, half here, here is like 3 sides. 1, 2, 3, right? I have to think about it. Hold on. Okay, so if we cut it on top, we cut it in half. So we got rid of half, right? We got it here, we got rid of another half, right? So half of a half is a fourth. And then next part is an eighth. So then if it's an eighth and we have 8 sides, then the total should be 1 atom, right? So make sure I'm telling you right. Yeah, they can combine into one because each section is an 8. It adds up to an 8. Yeah. So like, yeah. So all of this, these top would combine to be a half, yes. And then this bottom would combine to be the other half, right? So if we sit there, like I said, if we sit there, we did it, right? First off, we'll take it, cut it in half, right? That will be the side, okay? Then cut off the top, right? And then we'll cut off the front face, yeah. Because remember, it's a 3-dimensional structure. Okay, this is just showing you the same thing. Now, if we wanted to calculate, and this is sort of what they used to sit there and make the calculation, the distance from an atom is that if it's an atom and it's behaving properly, then it's going to be the radius. The length of that unit circle is going to be the radius 2 times the radius, right? Okay, so this here, okay, so a simple cube is the simplest possibility. Funny thing is that you don't get too many of the solid set formed. There's very few, right? Body center and face center are what are more commonly formed. Body center means that you also have a cube in the middle as well as cubes on the lattice. So you have, not a cube, a sphere in the middle as well as spheres on the lattice points, okay? Face center means that you have on each side, there's a sphere. So there's a sphere here, there's a sphere here, sphere here, sphere here, and a sphere here, as well as a sphere at each lattice point. Okay, so in the case of body center, the spheres at the lattice points are not touching each other, right? Just they're touching the center. Okay, so if we look at the, and let me show you another picture, a better picture. Right? Center point. So you guys see here where these guys, they have gaps between them, but technically these guys would be touching. Okay, the center one would be touching. Okay, are you with me so far? Okay. So if we were trying to measure the length of the sides, it's going to make it a little bit harder. We could actually use that diagonal, right? So going from one end to the other end. So then that would be, this here would be the radius, this would be the diameter, and then that would be a radius, right? And so then we could use that diagonal, once we have that diagonal, we could use that to sit there and calculate what this side is. Okay. Yep. And then that would be the radius, right? Okay. So we have, in that case, it'll be what, 2D, right? Okay. And so, and if we remember from, if you guys remember, what was it? It's opposite over hypotenuse, right? Is sine is opposite over hypotenuse. And so we know that if we measure that angle, right, this here represents a hypotenuse, then we could sit there and use that to calculate the length that was, okay? Now this guy, this is face center, right? So in the case of face center, now we have an atom in the center of that. So again, these guys are not going to be touching each other. You're going to have a big atom that's going to be right there in the middle of that, right? And that's going to be that's going to be different than what we saw with body center. Okay. So in this case, again, here's our diagonal. So then this one will be easier rather than taking the diagonal of the cube itself. So you just have to look at the face, and then you'd be able to calculate your angles here. I mean your lengths. Okay. Okay, so it can get even more complicated, right, than what we have here. So this here is this is a cubic closely packed structure or CPP arrangement. So we have layers. So it has layers of organization. So it's organized ABC, 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 and this is an octagonal shape. Okay. This here basically showing you the same thing. Our layers of ABC, ABC, and then I'll have another layer of ABC. Okay, so these are a hot mess, right? They're going to have coordination numbers associated with them. They still can make calculations, but the calculations are going to take a lot more work to sit there and get to the point. Okay. So this is what I was talking to you earlier. So this length here is going to be 4R or 2D, right? And so then we're going to have to use the angle to sit there and calculate the sides. So when you're calculating, so this would give us it would help us calculate the distance from an atom to an atom, or the distance of an atom, right? So here, if we look at it, this is going to represent, if we want to calculate the radius of the atom itself, right, we'd use these type of measurements. Right? That's right. Because it's a cube, we know that this is going to be a right angle. So we know that the sine of 90 is opposite. So here's our angle. Maybe opposite over hypotenuse. .89. Oh, wait a minute. Are you looking at, did you change it to radians and not? Yeah. I just assume that. Yeah. Should be one, yeah. Yeah. So, but we can actually use that, right? To sit there and figure out our calculations, right? So, because it would be, or you could use a squared plus b squared equals c squared, right? And that's going to give us right. Where a and b, in this case, it would be a squared, so it's 2a squared equals 4r, right? A squared, that is all right. A squared, 2a squared equals 4r squared. And so then we'd be able to calculate what A is. All right? Because based upon a right triangle, A squared plus B squared equals C squared. So you guys do remember that? And so then we would be able to calculate what each of the sides are, right? The length of the sides. And then you, in theory, if you know the length of the sides, or if you're given the length of the sides, you're able to calculate the radius of the atom. Okay. Okay. Here, this is just showing us that the angles, we know that each of those are right angles, but this represents the angles. Okay. And these are the 7 different lattice systems. Okay, so we have the cube. So these are the examples of the cube. This guy is the, I can't even read it because it's so tiny. The tetragonal. So we have simple and body center. This here is orthorhombic, and then this one is monoclinaic, and this one is triclinaic. This is hexagonal. This is rhombohedron. Yeah. Yeah. And so, as I said, they get a little more complicated as we go. Okay. Okay, and this is just showing us that when we're talking about those cations and those anions and how they would organize themselves depending on the structure that they're in. So here, this is just showing that a cation may occupy 2 types of holes between an anion. So it could be an octahedral hole or a tetrahedral hole. And this is just showing us the distinction between the two. So this is our tetrahedral hole. This one here is our octahedral hole. So this here represents like the positive. There's the anion. So our positive, our negatives, our positive, our negatives. So there's different possibilities that could exist. So it's going to be kind of dependent on the cation's size and the shape of the hole that's going to be occupied in terms of how it's going to be organized. So is it going to be a tetrahedral hole or is it going to be an octahedral hole? Well, that's going to be dependent on the size of our cation. Okay. Questions? Concerns? Kool-Aid. Okay, what are we doing on time? Okay, so this is just another example of our face center. This here is sodium chloride. So we have, in this case, very nice lattices that are established. You remember face center is that each of the sides have an atom in the middle of it. And here, the lattice points. We're alternating between our lattice points, and then we have atoms in between. This here is an example of zinc sulfide. Okay, face centered as well. Zinc molecules, the sulfur molecules. And then you have the zinc that's going to be in between those. This one here is a calcium fluoride face center. Yeah. So the structures get pretty cool, you know, and you sit there and you think about it, and then how they interact with each other are going to play a part in that. So, okay. So, and this is just showing you earlier how we would go about calculating using our triangle. A, this guy is going to equal 4A. So we'd be able to sit there and use that to sit there and calculate what each of the A's are based upon the radius of the atom that we're working on. Okay. So when we talk about those wave structures, you guys remember constructive and destructive interference. Constructive basically is going to reinforce, so then our magnitude is going to get bigger. Right? Destructive is going to cancel out, so we're going to have a flat line. Okay. So when we're using X-rays, we could actually use that to our advantage to sit there and try to figure out the distance between two atoms. So we'll use an electron wave, an X-ray wave, and how it scatters once it hits the atom, because you shoot the X-rays in, it'll hit the atom and it should bounce off of that atom. Okay. So if it's constructive, we're going to get this nice little structure. Destructive, we're going to end up losing some of those angles. Right? And so this here represents the distance between the atoms. Here, this is the angle. So the angle which the X-rays are going in. And so, as I said, we could actually use that to sit there and calculate the distance between the two atoms. Okay. And this is just showing you the diffraction of X-rays. Those are crystalline materials. And so this here shows us the diffraction point. So we're able to sit there and use that as means of calculating the distance between the two atoms. Yes, it is sort of similar to it. But in that case, they're using alpha particles. Yep. Okay. And this is just showing you an X-ray diffraction. Okay, we're going to stop here. The rest of it is just symbols for exercises. They should be open. If they're not open, let me know. Okay, so we're going to actually stop at this point, and then we're going to get started with the lab so you guys can get the lab done.